Put 2 fingers on the front of your shoulder, just under the collarbone, and roll your arm backwards. Feel that. There is a hollow there, and inside it, your arm bone is sitting in a socket so shallow that the joint is barely holding on. A chimpanzee has the same bones in the same places, same collarbone, same socket, same tendons crossing the same gap. The angles are a few degrees different. That is the entire difference. And because of those few degrees, you can hit a target 30 meters away, and a chimpanzee that could tear the door off your car cannot reliably hit a wall. Here's the number that should stop you. When a trained human throws, the upper arm rotates at around 9,000 degrees per second. That is the fastest motion the human body is capable of producing. Not running, not punching. That one twist in the joint that is barely holding on. So how does the weakest ape in the family end up owning the planet? And what happened to that machine once we stopped needing it? Every layer of this gets stranger than the last, and the last one is happening in your shoulder right now while you sit still. Let's go. Let's start with how weak you actually are, because the real number is smaller than the one you have been told, and that turns out to be the whole point. You have heard that a chimpanzee is 5 times stronger than a person, or 6, or 8. Those numbers come from a single story about a chimp in the 1920s pulling on a rope, and they have been repeated ever since with nothing underneath them. In 2017, Matthew O'Neill and his colleagues finally did it properly. They took actual chimpanzee muscle, measured the force the fibers produced, and compared it directly with human muscle under the same conditions. The answer is 1.35. Chimpanzee muscle is about 35% stronger than yours, gram for gram. 35%, not 500. If a chimp were genuinely 6 times stronger, it could deadlift a small car, and it cannot. So where did 5 times come from? From one man with a rope. In the 1920s, a biologist got a few captive chimpanzees to pull on a dynamometer and published readings that suggested enormous strength. The problem is that a motivated chimpanzee pulling with its whole body and both arms was being compared against a person pulling politely with one. In 1943, another researcher repeated the test more carefully and got numbers barely above human. The careful study is the one nobody quotes. That is worth sitting with for a second. A single, badly controlled measurement from 100 years ago became a fact that everybody knows, and it survived because it makes a better story than the truth. The truth is a 35% edge, and the truth is more interesting, because a 35% edge is a trade you can actually afford to make. But hold on to that 35%, because it is not free, and what we paid for it explains everything else. The difference is in the fibers. Muscle comes in 2 broad flavors. Fast fibers contract hard and quickly, and then quit. Slow fibers contract gently, and keep going almost indefinitely. Chimpanzee muscle runs at roughly 2/3 fast fibers. Human muscle runs the other way, mostly slow, and the exact ratio shifts with training and with which muscle you look at. Their fibers are also longer, which gives more travel per contraction. So a chimpanzee is built like a tool designed for one violent effort. You are built like a tool designed to keep going after the violent effort has ended. Now watch what happens when you follow that trade all the way down. Because you cannot generate force, you got everything else. You have between 2 and 5 million sweat glands, more per square centimeter of skin than any other primate. On a hot day, you can shed more than 1 liter of water an hour through your skin and keep your core temperature stable. A chimpanzee cannot. Its cooling system is panting and shade. Push a chimpanzee into open sun and make it move continuously, and its body temperature climbs until it has to stop. Push a human, and the human keeps walking. Then there is the tendon in your heel. Your Achilles is long and thick and behaves like a spring, storing energy on each footfall and returning most of it on the next step. A chimpanzee's equivalent is short and stiff, which is excellent for climbing and useless for covering ground. And at the back of your skull, running down into your neck, there's a small band of tissue called the nuchal ligament. Daniel Lieberman and his co-author pointed out in 2004 that you share this feature with horses and dogs and hares, and not with chimpanzees or gorillas. It exists to stop your head from bobbing while you run. It is a piece of hardware whose only job is running, and no ape except us has it. So the picture is already strange. We are the ape that gave up force and bought heat tolerance and range. Here's what that bought in practice. In the Kalahari, a handful of hunters have kept a technique that almost nobody else on Earth still uses. They pick an animal in the middle of the day, in temperatures over 40 degrees, and they simply follow it. They walk and jog. It sprints again, shorter this time. They keep coming. Louis Liebenberg documented these pursuits in detail, and the numbers are consistent. Between 2 and 6 hours, 25 to 35 kilometers. And at the end of it, the animal stops because its body has run out of ways to shed heat, and a human who has been sweating steadily the entire time walks up and the hunt is over. No claws, no speed, no ambush, just a body that refuses to overheat, attached to a brain that will not lose the trail. Read that again because it is the strangest thing about your species. Almost every predator on this planet closes the distance and gambles on the outcome. We found 2 ways to avoid the gamble entirely, and the chase is only the first one. Because the chase only works on some animals, in some weather, in open country. There is a second solution, and it is the one that actually changed the planet. It is sitting in that shallow socket you touched at the start. Almost no animal can throw. This is the fact people find hardest to believe. Watch a chimpanzee throw, and it looks wrong, because it is throwing entirely with its arm, like a person swatting a fly. Best recorded speeds for a chimpanzee are around 30 kilometers an hour, and the accuracy falls apart past a few meters. A trained human pitcher reaches 145. That is not a difference of degree. That is a different machine. In 2013, Neil Roach published the anatomy of that machine in Nature, and the mechanism is not what most people assume. The power does not come from your arm muscles. Your arm muscles are not strong enough. If you calculate the force your shoulder muscles can produce and compare it with the energy actually leaving your hand, the numbers do not match. Something else is supplying the difference. The answer is elastic. When you cock your arm back, the ligaments and tendons crossing the front of the shoulder are stretched taut. They store energy exactly like a drawn bow. Then they release, all at once, and dump that stored energy into rotating the upper arm. Your muscles do not throw the object. Your muscles load a spring, and the spring throws it. Roach identified 3 changes that make this possible, and all 3 separate us from every other ape. A tall, flexible waist that lets the torso twist independently of the hips. A lowered twist in the upper arm bone itself, and a shoulder socket rotated to face outward rather than upward. That last one matters more than it sounds. A chimpanzee's shoulder socket points up and toward the head, which is ideal if you spend your life hanging from branches. Yours points out to the side. It is a worse design for hanging and a far better one for storing energy in a wind-up, which is where the second piece of evidence comes in, and it is not from bones. It is from a laboratory. Roach did not just describe the anatomy, he tested it. He brought in college baseball players, wired them for motion capture, and then strapped them into a brace that restricted one component of the throw at a time. Restrict the torso rotation, and the speed collapses. Restrict the shoulder wind-up, and it collapses further. Each restriction removed a specific storage mechanism, and each one showed up as lost velocity in the ball. That is the difference between a good story and a tested one. You can take a modern human, switch off one piece of the machine at a time, and watch exactly how much of the throw each piece was carrying. And the power does not start in the shoulder either. Follow the sequence backwards from the hand and it runs through the elbow, the shoulder, the torso, the hips, and it ends at the foot pushing against the ground. Roughly half the energy in a fast throw is generated below the waist and passed upward through the trunk like a whip. The arm is the last link in the chain, which is why a strong arm attached to a stiff torso throws badly, and why the biggest gains from training come from learning the order rather than from getting stronger. It also means the throw has to be learned. You are born with the hardware and none of the sequence. Nobody has ever picked up a rock for the first time and thrown at 100 kilometers an hour. It takes years of repetition to wire the order of that chain, which tells you something about how ancient groups must have lived. The machine only pays off in a society where you can afford to spend years practicing with it. Now, some of you are thinking, hang on, monkeys throw things at zoo visitors constantly. I have seen it. Fair question, and the answer is in the speed. Throwing something is easy. Throwing something fast enough that a large animal cannot react to it in time is not. The gap between 30 kilometers an hour and 145 is the gap between an insult and a solution. And the thing that closes that gap is not strength, because the chimp has more of that. It is the storage, which is the moment to say the thing this whole video has been walking toward. You were not designed to fight anything, ever. Not with your hands, not at close range, not once. Every trait in your body points the same way. The fibers that will not quit, the skin that sheds heat, the tendon in the heel, the loose socket in the shoulder. Not one of them makes you better in a struggle. All of them make you better at not being in one. So when did we get this? Earlier than you would guess. The shoulder anatomy that makes it work shows up in Homo erectus around 2 million years ago. The waist, the arm bone, the socket. That means the machine is older than our species, older than fire being used routinely, older than anything we would recognize as culture. What we do not have is footage. What we have is what people threw. In 1994, in an open-cast coal mine near Schöningen in Germany, Hartmut Thiema's team started pulling wooden spears out of waterlogged ground. 8 of them, spruce and pine, up to 2.3 meters long and about 300,000 years old. Wood almost never survives that long. These did because they were sealed in wet sediment with no oxygen. And they are not sticks. Each one is thickest and heaviest about a third of the way from the point, which is precisely where the balance point sits on a modern competition javelin. Somebody shaped these deliberately so that they would fly straight. 300,000 years ago, in a cold lakeshore in northern Europe, somebody understood weight distribution well enough to build it into a piece of wood by hand. Go further back and the evidence gets smaller and sharper. At Kathupan in South Africa, stone points around 500,000 years old carry damage patterns on their tips that match what happens when a point strikes at speed. Not cutting damage, impact damage. Then the upgrades start, and they never stop. Around 64,000 years ago, at Sibutu Cave in South Africa, points appear that are small and light and standardized, the signature of arrows. Around 30,000 years ago in Europe, the spear thrower arrives, a carved hook of antler or wood that acts as an extra joint in your arm and roughly doubles the range. Some of the surviving French examples are carved into animals, which tells you these were not disposable. And you can measure the latter. A spear thrown by hand is effective to something like 15 or 20 meters, and past that the accuracy is gone. Put the same spear on a spear thrower, and the effective distance roughly doubles, because the hook adds a second lever to your arm and the dart leaves your hand far faster. A bow pushes it further again, out past 50 meters, and it does it while you are crouched behind cover, rather than standing up and winding your whole body back. Each jump does the same 2 things. It puts more distance between a person and the thing that could hurt them, and it lowers the amount of body you have to put into the effort. 15 meters, then 40, then 100. The graph of human weapons is a graph of a species steadily removing itself from the scene. Every single one of these inventions is the same idea repeated. Keep the target where it cannot reach you. Add distance. Add distance again. And here is the thing about a body that solves problems from 30 meters away. It changes what the group can be. If your survival depends on close combat, then the strongest individual is the most valuable one, and everybody else is overhead. If your survival depends on a thrown point, then the person who makes the best points matters, and the person who reads tracks matters, and the person who remembers where the herd goes in a dry year matters. A body that fights from a distance can afford to keep people who cannot fight at all. There is one more comparison worth making, and it is with the cousins. Neanderthals were stronger than us by a wide margin. Denser bones, thicker limb shafts, more muscle attachment area, and arm bones that show heavy loading on one side. For a long time, the assumption was that this made them better hunters, and in close quarters it almost certainly did. But when researchers looked closely at the shoulder, they found the twist in the upper arm bone sitting at a different angle from ours. A 2009 study of Neanderthal arm bones argued that the difference points toward a shoulder better arranged for thrusting a spear held in the hand than for launching one. Their tools support the same reading. Neanderthal points are often heavy and robust, the kind you drive into an animal at arm's length, while the points that show up with our lineage trend smaller, lighter, and more standardized. The argument is not settled, and honest researchers say so. But hold the two pictures side by side for a moment. One group closes the distance, using a body that can take the impact. The other stays back and sends the point instead, using a body that cannot take the impact and does not intend to be there for it. One of those two strategies is still on the planet. So what took it away? The answer is simpler than you would like. A trigger. The chain is easy to follow because every step does the same job better. The thrown rock became the spear became the atlatl became the bow. Gunpowder reached Europe in the 13th century, and within 200 years, the decisive question on a battlefield was no longer how far a person could throw, but how fast they could reload. Then came rifling, then optics, then machines that put the object on target with no human arm involved anywhere in the process. Each step removed a little more of the body from the job, and the last step removed all of it. Now the price, in numbers, because it is your shoulder we are talking about. That socket you touched at the start is the shallowest major joint in your body. The ball is roughly 3 times larger than the dish it sits in. Nothing bony holds it in place. It is held by soft tissue, and that is the deliberate trade. Bone would be stable, and stable cannot store energy in a wind-up. The result is that your shoulder is the most frequently dislocated large joint in the human body. Not because it is badly built, because it was built loose on purpose by 2 million years of selection for a motion that most adults now perform roughly never. And we know the tissue still responds, because in the small number of people who do throw for a living, the adaptation is visible. Take an X-ray of a professional pitcher's throwing arm, and the bone itself is different from the other arm, twisted further along its length by years of loading during growth. The shoulder capsule loosens on the throwing side, and the range of rotation increases by a measurable amount. That is not damage. That is the body doing exactly what it did for 2 million years, on request, in a person who happens to be born in the wrong century for it. Which means the difference between you and them is not anatomy. Everything they have, you have. They loaded it and you did not. The machine is still installed. The job was canceled. We traded a shoulder that could end a hunt from 30 meters for one that gives out reaching into the back seat of a car, and most of us never even knew what it was built to do. Which brings us to the question worth asking. What if the ache in your shoulder is not a fault? What if that joint was made loose on purpose, and what you are feeling is a spring that has not been loaded in 20 years? The evidence points that way, and physical therapists have been saying a version of it for decades. The tissue in a shoulder responds to load. Stop loading it and it thins and stiffens, and then the first real demand you make of it, lifting a suitcase into an overhead locker, arrives at tissue that has forgotten the assignment. Our ancestors, incidentally, understood the maintenance requirement without a single study, because for them it was not maintenance, it was Tuesday. A person who threw for food threw constantly. You do not develop a 140-kilometer-an-hour arm by deciding to. The motion has to be learned young and then repeated for years, which means that in any group that lived by the throwing was practice, entertainment, and food all at once. The mark of a competent adult was an arm that could put a point where the eye was looking. And there is a detail in the archaeology that I find hard to get past. Those Schoningen spears were found with the remains of dozens of horses in a place where animals came to drink. That is not a chance encounter. Somebody chose the location, prepared the equipment in advance, and waited. The throw was the last 2 seconds of a plan that had been running for days. That is the part I keep coming back to. Not the strength, which we do not have, and not the speed, which we do not have either, The planning around a 2-second window repeated until it worked. So where does that leave you? Sitting still, with a spring in each shoulder and nothing to throw at. Your body is not a collection of weaknesses. It is a very specific set of trades, all made in the same direction. 35% less force per gram of muscle, in exchange for fibers that do not quit. Fur, in exchange for 5 million sweat glands. A stable shoulder, in exchange for one that can store and release energy like a drawn bow. Every one of those trades gives up power in the moment and buys reach. Reach in time, reach in distance, reach in how long you can keep going. You are not the strongest ape. You were never in the running. You are the ape that solved the problem from far enough away that strength stopped being the question. And that hollow under your collarbone, the one you can still feel if you roll your arm back, is not a design flaw. It is the loosest joint in your body, because a tight one cannot wind up, and something in your family tree needed to wind up so badly that it was worth being the ape that dislocates. So here's what I want to know from you. When was the last time you threw something as hard as you physically could? Not a toss, not a lob, a real throw. Tell me in the comments, and tell me whether your shoulder complained about it the next morning.